Good morning. If you can hear me, you can use the chat box. I hope you can hear me. No. Oh, yes. Okay, good. Okay. I hope you are well this morning, and thank you for joining me. Of course, I'm trying to balance the time of the session to accommodate more students, but I hope 11 a.m., like at lunchtime, almost a lunchtime, would fit more students, or maybe different students. Okay, just to, I want everyone have the option to join the session. Okay, that we've done with exam 1. Okay. Just a quick feedback. I think the exam went quite well. Of course, we always have some last-minute students that they are a little bit lost. Yeah, they email me like at 11:30 that they can't access the test. Of course, you can't access the test because you need 100 minutes, right? First of all, and you need examity appointment. Okay, that means I know most of you. I'm just talking about maybe 1 or 2 students. Okay, but everyone is really good. Everything went nice and smooth. The average is quite good, but we don't really share the average. And another thing, we don't really looking at the average. Okay, because average is not telling us much. We're really looking at the individual students. Because even if the average is, I don't know, like let's say 75, 80, if all of the students will have 80%, I will be so happy. But of course, we know what average means. Some students achieve high grades, and some students didn't. Yeah, that means the average is not really good from the teaching perspective. That means please do, of course we don't really curve the tests. Okay, everybody is working on like we call absolute scale. Whatever you achieve, that's your score. Okay, because we want to. That's how it works. Okay, let me just a quick feedback. You can of course email me, or you can put some. You can start some discussion on the class discussion, like about the test. How was it? I hope you were not surprised with any questions. The questions were almost identical, like the sample test, practice test, and of course the weekly assignments. That we will just carry on with the same style, the same manner. Okay, that's what we have today. Today I will start chapter 11. Chapter 11 is quite, how can I say, heavy, intense. Okay, chapter 11, that's what always probably built the reputation of Math 141. Sometimes I heard on campus that Math 141 is really difficult class. And I believe it's because of chapter 11. But again, if you will practice, if you will be honest with yourself, if you will put time, it's just a little bit new concepts, but you can still manage. Okay, that's me. Chapter 11 talks about the infinite sequences and infinite series. Okay, just section 1, the first section, 11.1, talks about the sequences, and I will introduce everything. And then next week we will start 11.2, the infinite series. Okay, and they are connected, of course, but it's a huge difference. If you will always probably ask me, oh, I'm so confused, because we have to be really careful what one thing means and then what the other thing means. Okay, let's start, because I shouldn't really take your time. It's just the lecture. And if you wish to make an appointment with me, like talk one-to-one about the test or about your current situation, I'm always available. You know that, because it's so easy. You can be wherever, I can be wherever, and we can always talk. Okay, everything should work well. I'm still testing lots of pens and lots of screens, but hopefully everything will be good. Okay, let's start. Okay, I will switch off the camera and I will move to my screen. Okay, sequences, that means what it is. Let's see. Really simple. The sequence is simply a list of numbers written in the definite order. And we can see we have a sub 1, comma, a sub 2, comma, a sub 3, comma, and so on. Okay, but we have to be, always, we have to keep the order. And then we call this, and we call this. That's my first slide. That means, of course, a sub 1 means the first term, a sub 2 means the second, and so on. That's important. A sub n is the nth term. And then, if we would like to define the next one, we have to simply say a sub n plus 1. It makes sense. 1, 1 plus 1, 2, 2 plus 1, 2 plus 1, 3, and so on. That we know that here, if I would like to list more terms, I will have n sub n plus 1, and then possibly a sub n plus 2, and so on. I know that probably seems so obvious and so like, oh, why she's even writing this? But believe me, it's important because we will operate, we will use that script, that index. Okay. Okay, and one more, because I didn't put this. Can you tell me how we will define one term before a sub n? Can you write on the chat box? Just as a first question today. Yes, a sub n minus 1, of course. Okay. Let me just do one thing. Okay, I think I'm good. Okay, that means this, yes, thank you for answering. That means this is, that's the idea. Okay, and then of course we will always deal with the infinite sequences, which this means that we will always assume that the pattern will continue for infinitely many terms. Okay, next one. Okay, before, of course, you know that always the first section in the new chapter is more theoretical, right? That means we will still practice, and I can show you what is the most important question out of this section, but we still have to go through the new terminology, new definition, new concepts. Okay, that means what we can also do, we can also call, let me come back to this one. What is also important, I'm using the letter n, right? N. That means please remember in mathematics, n, it's simply the natural numbers. Or we can call counting numbers. Yeah, like let's say I will count the students in the classroom today and I will say 1, 2, 3, and so on. Okay? That means it's a positive integers. Occasionally, because it's helpful, we will add 0. Okay, we will add 0, but of course, when I count my students, I'm not counting 0, 1, 2, 3. But for this one, we will say, this is like a 0 term. It's still a first term. It will be still the first term, but will be defined for n0. But you will see later in the chapter 11. Okay, but please remember, n is just the positive numbers. Then we can say that the sequence is simply a function whose domain is the set of positive integers. Yeah? That means we do have a special notation, which of course you did realize, a sub n. That's how we will recognize that this is a sequence. But we can also say f of n. And if we don't see, because f of x, of course, we always assuming that almost all of the numbers are in the domain. We do have some constraints, like x cannot be 0 and so on. But x is x. X is continuous, all of the numbers. If you see n, this means that it's just the counting numbers. Okay, just the discrete, let me say, because what we may have now we will define the formulas. That means I can even have, let's say, n squared. If I will think about the function x squared, I will just draw parabola. Yeah, x squared, we know that's x squared. But since I'm thinking about the n squared, I will follow the same path, the same shape, but I will only have 1 squared, 2 squared, 3 squared, 4, 5, 6, 7, and so on. Okay, that we'll have like a discrete mathematics, like just the dots. Yeah? The same shape, but just the dots, not the continuous curve. Okay. So we may call, but we will not say f. We will not say f of n. We will still keep the a sub n. But let's see how what other notation we have. Okay, that means this is the notation a sub n, and sometimes you can see these curly brackets. Okay, a sub n. That means that's my sequence. Or we may have more details. We may have a sub n, and underneath we will say we are starting with 1. Yeah, that's what and of course we go to the infinity by 1. 1, 2, 3, 4, 5. And that's what I'm saying. Sometimes you may see 0. Yeah, that means please do not be surprised, because 0, it is quite important number. And we will need 0, you will see. Right? That means we will still call the first term, but we will substitute instead of n 0. Okay. If nothing is written, can you see I put the question mark, then we always assume that it's 1. We always starting with 1, like counting. Okay, now let's look at some formulas for the nth term. Okay, we may have few different, 3 different ways. Yeah, we may have a preceding notation, defining formula, which they look almost the same, or we may have like expanded form. All of the terms is like written out. Okay. Let's see. So what I have 1, 2, 3, 4 examples. For example, the formula could be n over n plus 1, starting with 1 and of course go to infinity. Or yeah, instead of the curly brackets, I can use a sub n notation, but you can see it's the same thing. Or I can list all of the terms. If I put for n1, I have 1, 1 plus 1, 2, 1 half, 2 thirds, 3 over 4, 4 over 5. And of course this, yeah. Okay, let's actually try. Can you tell me what will be the next term? What fraction I will have for the next term? Because this term is definitely a sub n. Now we're playing with the exact formula. Do you think you can tell me the term a sub n plus 1? Just instead of, right? Yes, Alan, thank you. Instead of n, we have to put n plus 1. Okay, that means you saying about, okay, I can write this down. 5 over 6, but what I'm saying, we still have dots and we are here at the moment, okay? And now, from that moment, we're dealing with n, not really with the exact constant. That means after n over n plus 1, we have n plus 1 over n plus 2. Yeah, that's the point to understand. And maybe one more. That means this is, who can give me another fraction? Of course, we can go the whole night from the, what will be the next one? A sub n plus 2. Oh, just instead of n, we can put n plus 2. N plus 2 and n plus 2 plus 1, n plus 3. Thank you. I know, thank you, but it's I can tell you, it's important. It's important to have this idea. Okay. Oh, yes, that lines. Okay. Now let's look at the other, and the formulas, because you can see the formulas could be exactly the same like for functions. Like I just gave you like x squared or n squared. Yeah, please remember, the formulas could be exactly the same. Okay, my next formula is -1 to the n times n plus 1 over 3 to the n. That means this notation That's the same thing, different notation, and this is just the expanded form. Okay, for this example, we do have new part. We do have -1 to the n. Okay, that means this will be probably something different that we didn't see this for the function, yeah, for the x. Okay, that means you probably realize -1 to the power of n, which means -1 to the power of 1 will give me negative value. -1 to the power of 2 is giving me positive. Okay, that's, I was trying to write positive. And then -1 to the power of 3, negative, and so on. If the power is even, we have positive. If the power is odd, we have negative value, of course, obvious. Which means we're creating a sequence which we will call alternating in sign. That means positive, negative, positive, negative. So please remember that's, yeah, that's the like alternation part, -1 to the n. And the rest of them is just the same formula. Okay, n plus 1, 3 to the n. And you see, all of the formulas depends on n. If I will ask you to give me, for example, a 100, you can give me a sub 100. Okay, because you can say 101 and 3 to the power of 100. Of course, we will not calculate this. Okay, and the value is the term is positive because it's even. As we can see, all of the formulas depends on n at the moment. Okay, that's new. Okay, actually, I can keep this because that's important. Okay, another formula is square root of n minus 3. We may write like that, or we may just expand it. And now you can see it's obvious that we have to start, actually, because I was focusing on 0, we may also start from different number, because we have to respect the algebra is the square root, and square root is not taking the negative numbers. Okay, that means we have to start, of course, 3, it's the minimum number, and then all of the numbers greater than 3 will work. We will get positive. That means sometimes we have to adjust the starting point to the given expression. And that's the same. And let's look at one more, which I think I have 0. Cosine of n pi over 6. That means cosine of 1 pi over 6, cosine of 2 pi over 6, cosine of 3 pi over 6. Actually, I should say 0 pi over 6, which will be 0. That means this is also the moment that we're not starting from 1, especially for the trigonometric, right? Because trigonometrics, like, it's good to know what happens at 0. The same formula and the expanded form. That's the unit circle. Okay, that means just to give you the idea that we have a formula for the sequence. Sequence is like a function with the positive integers being at the domain. Okay, now let's practice a little bit. Okay. I will give you an expanded form. That means this is a sequence. I think I should maybe put like some curly brackets. That's the sequence, a sub n. And we have to look at the sequence, look at the pattern, and possibly find the formula. Okay. -1, +1, -1, +1. That means it's just the alternation. Do you remember from the previous slide how we can define the alternation? It's just -1. I don't know if somebody is typing. I don't want to be the first one. -1 to the n. Yes, thank you. That's what I was thinking that somebody is typing. Tyler, thank you. -1 to the n. If n is 1, then it's -1. If n is 2, it's +1, and so on. Also, please note that I can do maybe -1 to the n plus 1, and I am saying that I'm starting from 0. Also works, right? Because if n is 0, my first term will be -1 to the power of 0 plus 1, which is 1, which is still correct because I have to match my first and the rest of the terms. That means you may also, please do not be surprised that if we change a little bit of the index, we're still matching. Yeah, that means n or n plus 1. Or sometimes we can play with this. What I can say, n minus 1, but then I have to start from 2, I believe. Because what's happened, each of the exponent for the first term, this one, and this one, when I create the first term, this exponent must be 1. Okay? Or actually, it could be 3 also. Oh, because I don't want to say 1, just odd number, and then the pattern will stay. Let's say 4. Because if I have 4, 4 minus 1 is 3, negative 1 to the power of 3, it's still negative 1. Yeah? I mean, just to have idea, to be flexible, to be. Of course, we need practice to get this confidence. Okay, another one. Now find the formula for this one. I will put the curly brackets. 2, 4, 6, 8, 10, and so on. 12, 14. How can we find the formula for the even numbers? What do you think? Of course, I am assuming that we're starting with 1. Okay, if we put n plus 2, and if n is 1, we're actually getting odd number. 2n, yes, close. Mariana, that was close, yes, thank you. That's really good, 2n. And of course, I can say 2n plus 2, 2n plus 4, 2n plus 6, if I want to play with the starting point. That's really good. Remember, 2n, yeah? Because whatever I'm saying now, we will use for the entire chapter 11. Okay, 2n as simply the even numbers. And now, probably I am really predictable. Let's find the formula for the odd numbers. This is missing. 1, 3, 5, 7, 9, 11, and so on. What do you think? What will be the formula for the even numbers? What is the difference? I was going to say, what is the difference between even number and the odd number? It's always 1. That's what we can say. We can say 2n plus 1, or actually Tyler gave us 2n minus 1. Both of them are good. Depends what we're starting. And now you will tell me, what n shall I put here? What n value shall I put here? 0 for the first one, really good. And for the second one, well, yes, really good. Because when I put 0 for the first one, I have 1. And then 3, 5. If I put 1, I will have also 1. Yes, really good. That's you can see. You can, of course, we have to have a basic knowledge, like what we're doing. But yeah, I want you to be confident with this, because you will probably ask me later, oh, why this is n equals to 0? Why this is n equals to 1? You have the answer, right? Yeah. Okay. What else I have? Oh, okay. I have just like a kind of random formula, crazy formula. But let's try. Let's look at the pattern and maybe we can try to find a formula. Okay, first of all, what we see plus, minus, which means I know that probably everybody knows this, but I will tell you that this is that part, -1 to the n, because the terms are alternating. And then we can focus on the main number. 3, 4, 5, 6, 7, and so on. That means, what do you think? How can we define the top numerator? Depends what we're starting, right? Like, let's say, okay, let's say, I will make it easy. Let's say we're starting with 3. That means what I can simply put on the top? If the first term is defined for 3, and then the second will be defined for 4, and so on, I can simply put n. No problem, that's n. And now, what do you see in the denominator? 5, 25, 125, 625. Of course, that's huge numbers, but probably the first 3 will give you an idea. This is 5 to the power of what number? Yes, okay. That means we have to, okay, it's 5 to the power of 1, 5 to the power of 2, 5 to the power of 3. That's what I have to do. I really have to say 1. How can I adjust my numerator? Because I don't want to have 1 on the top for the first term. And yes, thank you. That means instead of putting 3, I am matching the number to the starting point. Okay, good. That's good also. But if we would like to keep 3, this is, yeah. Okay. Let's say we would like to keep 3. How would you adjust? I typed my answer. How we can adjust the power, the exponent of 5? Because we really need, yes, because we really need 1, which means 3 minus 2 will give me 1. Yeah, good. Okay. Yes, so that's good. Okay, let's keep moving because it's a relatively long session. If I will not finish everything, of course, I think I've already posted like a practice with Kasia with some items from this session, but I will tell you later. I mean from this section, because session it's still on. Okay, that's also important. So far, I was showing you the formulas, yeah, like in the formulas for the sequence, like A sub n, and everything depends on n. Like let's say n plus 1. I think that was one. And when I asked you for the formula, like let's say even 100 or 1000, you can substitute instead of n 1000 and give me the value. But what we also have, we have a sequence, the formula for the sequence that is not directly defined in terms of n. It's defined a little bit different, and the name of this, it's we calling that we do have a recursive definition of the sequence. The sequence is defined recursively. And what this means, one of the sequence that is defined this way, it's the Fibonacci sequence. You probably heard about this golden proportion and these golden numbers. Okay, that's me. Fibonacci, of course, one of the Italian mathematician, long time ago. Okay, and just because to honor his name, instead of A, we're just using F sub n, F sub 1, 2, 3, but it's the same thing. But you may notice this is the main formula. And what this means, defined recursively, the formula for the sequence is defined in terms of the other terms of the sequence. Okay, that means you can see we see some terms, like the F sub n, it's defined as a F sub n minus 1 plus I'm just getting emails, plus F sub n minus 2. And I hope we understand what n minus 2 and n minus 1 means. Okay, but I will show you. And of course, having something like that, we always need some initial stuff. That means the first term is given, it's 1, and the second term is given, is also 1. And now, how can we read the formula? That means this formula, the way that is defined, it's a little bit complicated, because when I will ask you to find F sub 100, yeah, that's not easy, because then I need, if n is 100, I need n minus 1, which means I need the F99, F sub 99, and then minus 2 is 98. That means I need the term 99, addition of course, and I need the term 98, and I have to add them together to create 100. Yeah, that's what we can see. We probably have to have all of the terms before 100, which is not the case if the sequence is defined, let's say, a normal way, yeah? Not this fancy way. Okay, but now you have the idea how we can create the terms. In order to create the term, because I kind of pick n100, in order to create a term, I have to take two terms in front of that, yeah, and add them together. That means if the first term is 1, the second term is 1, can you tell me the third one? In order to get the third one, we have to add these two. Yes, 2. Now, what is the next one? What is, yes, 3. What's the next one? 5. Yes, we just adding the terms. 2. Okay, maybe a few more. I'm just testing your arithmetic. What is the next one? 8. Really good. What's the next one? 13. Really good. Maybe another one? 21, and maybe one more because I still have room. 34. Okay. Yeah. Okay. That's it. I think I type a little bit. Yes. Oh, I just reached 21. Okay. Yeah, that we can see. It's still good. You still have terms. You can still expand it. Yeah. But we can't really like play with the direct. Like if I will ask you what is like the 5th term, the 6th term, you have to have the chain before. Yeah, that's just this way. Okay, and now maybe like I can spend maybe 2-3 minutes talking about the Fibonacci sequence, because even if you're looking at these numbers, 1, 1, 2, 3, 5, 8, 13, 21, you will think, wow, okay, it's just a formula, just a theoretical part. And it's probably just happening in this classroom and it's just the random numbers. But of course, they are not the random numbers. The formula is so beautiful, and I would say, it's like, because what we have, this pattern, these numbers, we can see everywhere. Okay, it's like a golden numbers. Yeah, we kind of like connected. Okay, and I can show you. I have a few examples, but if you will Google Fibonacci sequence, you will have a multiple like applications and connections to these numbers. Let's see. First one, I just draw it. I'm sorry, it's weird. Okay, you can even look if you have a window. You can even look now. If not, if you will go for a walk today, you can like observe a tree. Okay, you can look at the tree, and you can see how the tree is growing. That means first of all we have like a one branch, like a root, one branch. Then at the certain level, it's expanding. I mean, it's divided, and we have 2 branches. And then at the other level, one branch will stay and only one will expand, and we will have 3 of them. And then you can see one will stay, 2 of them will expand, will be divided. We will have 1, 2, 3, 4, 5. And then of course 8, 13, and so on. And that's true. I know that in these days we have lots of mutation and lots of different things, but I'm sure you will find at least 1 tree like that. Yeah? All of them should be like that. They growing like that. They have this pattern, and it's unbelievable. That's the reason that mathematics is so beautiful. Okay, we are all connected. Remember, through the numbers. Okay, that you look at this. I just draw it. Of course, you can find the pictures on internet, but Okay, what else I have? Oh, that's scary. I have to find better picture. Okay, the proportion in our body. Okay, like if we will look at some bones, like that's the hand. This is kind of like, let's say, it's not really like I can't say the units, like inches or centimeters or any other, but like whatever units. If this is 2, this will be 3, and then this will be 5, proportion. And then 8, and then if you will reach, of course, that's like the bones. You can even look now at your hand. We have bones here. Yeah, like this is like the bone almost. And then the next one will be 13. It's probably the bone a little bit closer. We do have a bone, kind of like here. We have a bone in our hand. And then probably the elbow is the next one. That means if you will measure this, they also keep this proportion. They all keep these numbers. Okay. And then, yeah, this one is a little bit different. Let me skip this because this one we will, let's look at this. That's the thing. because this is telling me, yeah, the 1.6, 1.7 proportion, but I can also, I didn't put the numbers, but it's also here. Maybe let's look at this. When we will take, okay, one thing, look at this rectangle. If I will ask you now, like take a pencil, take a paper, and draw a rectangle, okay? You will draw a rectangle like that. Probably, yeah, random rectangle. Everybody will draw a rectangle, okay? And now, if I will ask you to measure size A, let me use different, because we do have A and B. Let's say X and Y, yeah? I will ask you, take a ruler and measure X and Y, and then divide. Of course, everybody is at different place at the earth, right? And we're not seeing each other. What you will get, you can even try. Yeah, you can even try. You will get like everybody will get approximately 1.6, 1.7. Yeah? That's also a beauty. Yeah? Like everybody will draw a random rectangle and the ratio will be like this. Okay, and of course, if you will fit like this, this is like kind of like, yeah, if you will fit these squares, you have these numbers. Yeah, we can see 1, 3, 3, 5, I mean 1, 2, 3, 5, 8, 13, if we will draw this way. And also this thing, this shape, the spiral, it's like the shell. The shells, when you on the seaside, the shells, they also have the same size. Okay. Also, what is the animal called? Snail. Yeah. Do you know the top of the snail? Am I right? You can help me with English. Also has this, yes, snail. Yes, snail. Thank you. Thank you. Yeah, the snail, they also have something like the spiral, also holds this proportion, these numbers. And of course, our rectangle that I was telling you. Yeah, that we do have plenty of application of these numbers. And I think I have one more. Oh yeah, like mathematical. We know Pascal triangle, the numbers, and then when I will take this like diagonals, this is giving me 1, this is giving me 1. If I add them together, I have 2. If I add this, because this is also no, I am kidding. This is 3, 1 plus 2, and then 1 plus 3 plus this is 1. It's 5, and so on. That means you can see 1, 1, 2, 3, 8. 5, 8, 13, and so on. That's when people as mathematicians, they seeing these numbers everywhere. And they exist. Probably that was the reason for this formula. That was the discovery of Fibonacci. Yeah, the Italian mathematician. Now you will know. Okay? And okay, let's come back. That's end of funny things. Let's come back to our content. Okay, I hope you will remember the Fibonacci sequence, the golden numbers, and please look at the tree, because I always, when I walk, I always look at, and I found the tree that is growing this way. Yes, I know the genius. Actually, the whole group of mathematicians, of course, Leibniz, Newton, who discovered calculus, they are also like a genius for that times. Yeah, that's amazing. Now we're just using, we're just trying to learn what they discovered. But yes, Fibonacci was a genius. I agree. Okay, but let's play a little bit with this recursive definition, and let's just calculate 4 terms. And the definition is like that. It's a little bit, we can see weird. The term n plus a sub n plus 1 is defined as a half of the term a sub n plus 2. Did I type? No, I didn't type. Okay, that means what we can do, we can start. The first term, of course, is given. Always something must be given. A sub 2, it will be 1/2 plus 2. And who can tell me what term shall I put here? Because if this is 2, this is 1 less, 1, right? a sub 1. Okay, that means we do have 1/2, 3 plus 2, 5/2. Okay, and let's, because they asking for 3, what shall I put here? Yes, the a sub 2, which is that term, 5/2. Oh, okay, a little bit of fraction. 5/2, 4/2, 9/2 times half, 9/4, and maybe one more. 1/2. And what I have to do here, of course, put the a sub 3. Oh, who can compute this for me? Oh, yeah, this, my pen is doing these lines, but okay, I'm not complaining. 9/4, this will be 8/4, which is 17/4. You can just check if my arithmetic is correct. Okay, I think it is. Okay, that we can see that's a little bit like, not complicated, time consuming to get the terms, but we know, you know the kind of definition. Okay, you're learning a lot, good. What else I have? Okay, that's me now. Let's come back to the normal definitions. Yeah, that's the sequence n/n plus 1, relatively nice. Because what I was telling you that we do have a formula, we have expanded form, but since it's kind of like a function, we can also plot these points. That's what I kind of did for the n squared. I plot the dots. That means that's actually what it is. We may use the number line, but I can tell you we will not do the 1D, we will do 2D. Because I can say, oh, this is my first term, 1/2, and then this will be 2/3, 3/4, and so on. And of course, we're getting really close to 1. But what we will do this way, okay? On the x-axis is actually n, and then a sub n is the output. That's when we have for the first term, it's 1/2. Yeah? The second term is 2/3. Oh, I'm not gonna squeeze it. And so on. And then it's 3/4, 4/5, 5/6, 6/7. And now, that's the main question for this section. We have to find out the behavior of the sequence, how these terms behaves at infinity. Okay? If infinity is involved, we will use the limits. That means limit as n goes to the infinity, of course, positive infinity only, because we're not talking about the negative n. No, we don't have negative n. And how this is behaving. Right? And what do you see? Do you think the numbers are getting bigger and bigger? I mean, they're getting bigger and bigger, but are they expanding like they will be huge numbers, infinity? Or do they have some limit? 5/6, 6/7, 7/8, 99/100, 101/102. Yes, that's we can see. They're getting bigger and bigger, but they will never be greater than 1. That means this behavior is just 1. The limit is 1. Okay, that means that's the main thing for this section. Find like how the sequence behaves. Okay? And as I said, we will not do this. We will always, if we have to plot, yeah, we will always use this 2D graph. Okay. Before we practice limits, let's learn a few new terminology. Okay, that means that's what it is. Yeah? The limit as n goes to the infinity of the sequence a sub n is L. Of course, yeah, we're reading this way, but you know calculus 1. That's the way. And now, that's the new words. If the limit exists, that L number exists as a finite number, we will say, okay, that the sequence is convergent. Sequence converges. convergence means it's like, it's limited. It's approaching one finite number. Otherwise, if we have the situation that all of the terms of the sequence are going like to the infinity, like for example, let's check a limit of the sequence, maybe just n squared. Yeah, like 1 squared, 2 squared, 3 squared. I can plot the numbers. That's what I was plotting. 1 squared, 2 squared, 3 squared, 4 squared. Of course, let me use something, they built the parabola, but we're not looking at the yellow. We know the pattern. I mean, we know the shape yellow, but we're only looking at the dots. That's what do you think? These dots, do they have a limit, the finite number as a limit? Or they going to the infinity, they expanding to the infinity? Yeah, that means this is definitely infinity. It's huge number. Yeah, going to the infinity. Thank you, Jake. In this case, if the answer is infinity, we will say that the sequence is divergent. The sequence diverges. I mean, now, from now on, we know the terminology, convergent or divergent. Or also, if you will say the limit is undefined completely, because sometimes we can't even say infinity. Yeah, we can say it completely doesn't exist because it's like doing weird things, our terms. Then there's also divergent. Divergent, like no, not defined. Or divergent means, of course, like big, huge numbers, infinity, no limits. Okay. And this is just like an example that we may have, yeah, like something like this, definitely the dots. I don't have the formula, but I have the dots. And of course, the dots represent my sequence. And we can see how nicely at infinity they approaching a line L. The limit will be L. Or we may have this formula, probably is crazy. We can kind of see like I will always call snake. It's getting like closer and closer. That means also for these dots, yeah, not the yellow. The yellow I'm just showing you. Yellow is just like a function, but we're looking at the dots, at the terms of the sequence. They also approaching L. As I said, formula will be quite complicated, but still, yeah, it's the limit L because it's tending to be closer and closer to L. Okay. Oh yeah, that means that's what I just was saying. That's my dots, and this is the limit. And yeah, because I follow your textbook, I don't want to miss anything. This is, of course, that's only the message. The rest of them, you know. Don't worry, it's just maybe too mathematical. If the limit of the sequence is infinity, the sequence diverges. Okay, and now, in order to compute that limit, of course, we can think that our sequence is like a function. That means we will adopt, probably, I don't know, I put chapter 2, but it's chapter 1. That's calculus 1. That means if you have a big textbook, you can probably go and check. But computing a limit of the function, we did have some properties, some laws. And now we are adopting them. We can completely take everything the same. And instead of having a function, the x, we will have n, the sequence, but we're doing the same thing. This is probably obvious. Limit of the sum is sum of the limits, difference the same. Having constant, we put in constant in front. Limit of the constant is just constant. And then a few more. Limit of the product is the product of two limits. Limit of the quotient is the quotient, remembering that denominator cannot be 0. If it is 0, we know what to do. You just learn the L'Hopital rule and so on. Limit of the power function is just the power of that limit, if the function is continuous. Yeah, just a few properties. And also we do have, the squeeze theorem is quite helpful. If we have this relation, okay, like one function, of course I should say sequence. A sub n, B sub n, C sub n. C sub n is the highest, A sub n is the lowest, and then we have something between. And then if the top and the bottom, the highest and the lowest sequence has the limit L, the middle one is forced to have L. Okay? Even if we can see it's quite complicated, probably some trigonometric formulas, but if I know C sub n, A sub n, don't worry, I can simply say B sub n has the same limit, because we can see it's squeeze. Okay, that means now let's try. Okay, before we start, before we try, because I have a few sequences that I want you to compute a limit. And probably after these limits, we will finish the session, but I can tell you what is missing and you can check, practice with Kasia. Okay, that means all of the previous slides were showing you the old properties that you know, and we do have one new properties that we will use. And especially because one new thing is -1 to the n. Yeah? Do you remember? This is kind of like a new for the formulas, and it is part of the formulas sometimes. That's what we have. Yeah, we have to just remember this. If the limit at infinity of the absolute value of the sequence is 0, then the limit of the original sequence is also 0. Okay, that's it. But please remember, this is only 0. Sometimes we overusing this, and if you getting, like, let's say 5, a different number, then you're assuming that this is also 5. No. Okay, that means this only works for 0. And when we can use it, as I said, probably when you can try, if you don't know what to do with that limit, you can try and apply the absolute value if you see that part, -1 to the n. Okay? That means, for example, let's find a limit at infinity of -1 to the n over n. Okay? We can see if I would like to expand this, let me write maybe here. That's my sequence. -1 to the n over n. Who can tell me the first term? Who can tell me the first term? You can just substitute instead of n1. It's -1. What about the second term? Positive half. Good. The next one? Yeah. -1/3. Really good. And maybe one more? Positive 1/4. Yes, okay. That's you getting this. Good. That's we can see. We have -1, they alternating, and possibly you may see what is the limit. Maybe we don't even need to use this property, because when I will plot these points, I will have -1, and then I will have half, and then I will have 1/3, and then I will have, -1/3, and then positive 1/4, -1/5, positive 1/6. When I will do my yellow to see the pattern of the lines, yeah, we can see closer. What do you think? What is the limit? The terms alternate, but they really nicely approach one number. They're getting smaller and smaller, of course. The limit is 0. The limit is simply 0. The limit is 0. That's we don't even have to. But let's see if you will decide to apply -1 to the n over n, and then you see, okay, -1 to the n, she said I can probably try absolute value. When I try absolute value, okay, n is positive. That means n will stay. -1 to the n, taking absolute value, would just become +1. And what is the limit 1 over n? You can think 1 over x. 1 over big number, 1 over infinity, of course, is 0. And then, yeah, thank you. If the limit, if the absolute value is giving me 0, then the original one also has 0. But you knew this before. Okay? That's the way to use it. The most confusing example, and I can say the most missed example, I can show you Do I have? Okay, we know this. That means we don't even have to answer this. But let me, now you may write this down somewhere. Put next to your bed and look for the next 3 weeks. Okay, find a limit. Oh, no. I'm sorry for that lines. It's not me doing, it's just my pen. Okay, -1 to the n. No, first of all, I want you to answer. That's me. Okay, let me ask this. How this sequence behaves? A limit at infinity and maybe 2n plus 1 over 3n minus 5. Do you remember the limits at infinity when we dividing the rational functions? I know that it's infinity. Yes, of course. That's my point. I know that this is infinity over infinity. You can still use the L'Hopital rule, but we don't have to. When we have a ratio of two polynomials, and if the degree is the same, we can just take the ratio of the leading coefficient. Great. 2/3. Okay, that means you're okay with this. Now, the question. How at infinity this sequence behaves? Let's say 4n minus 1 and let's say 7n plus 9. And this is together. This is together. It's -1 to the n. That means, what do you think? What will be the sequence? Is the sequence convergent or divergent? Of course, when the limit exists, it's convergent. Because I didn't use that. Yeah? That's what we can do. Again, you can think, oh, I do have the alternating part. That means one term will be positive, one term will be negative, positive, negative, positive, negative. But do they really create this snake, and do they really approach a 0? Yeah, because that's the only option for alternation. And let's see. What I will do, if I will be you, I will apply my new property. I will apply the absolute value. Applying the absolute value, my formula change. Okay, -1 to the n becomes 1. That means it's gone. And 4n minus 1 was positive, then will stay positive. And this is positive, will stay positive. Absolute value of positive number is positive number. Okay, can you tell me now what is the limit? You know now, because I know the -1. It's just, of course, ratio of the leading coefficient. Excellent, 4/7. Okay, that means having 4/7, what we can say about the original limit? Does this limit exist? I can just copy for you, because that's important. I don't want you to miss a point. As we can see from that part, we have 4/7. From this, which, let me come back to this. If this is not 0, then this is also not. If this was 4/7, I can't just say 4/7. I can assume right away that my limit doesn't exist, okay? Because I can show you why. This is 4/7. This part is giving me positive or -1, which means theoretically, just theoretically, the answer is positive 4/7 and -4/7. Positive 4/7, negative. That means the terms alternate, but that's n. They're not getting closer to 0. Yeah? Of course, we will have some terms. I don't want to plot the terms somewhere here, but at some point, at infinity, it will be positive 4/7, negative 4/7, positive 4/7, negative, positive, negative. That's, we can see it's like an oscillation. And that means this is what you have to think. Of course, we're not writing. We're just writing that the limit of this sequence doesn't exist. The sequence is divergent. Divergent. Okay, I'm testing my pen. Okay, that means please remember, because if you will have multiple choice option, you will see 4/7, you will choose 4/7, and you will go to the next question. No, not if you have -1 to the n. Okay, are you gonna promise me that you will double check and you will not pick the ratio of the leading coefficients? Think twice if you have alternating one, okay? And I will check your answers for your weekly quiz and the midterm too, okay? Do not miss this nice question. 4/7 is not really the answer. It's answer for this, but doesn't work because it's like oscillating. Okay, I know that it's 11 o'clock, I mean 12. Let me see what else I have. Okay, we have a question. So does it technically exist then if considered divergent? Oh, no, if it's divergent, it's just divergent. No, the limit doesn't exist. We have the terminology. We're saying that the sequence is divergent, but no, this means also the limit doesn't exist. Sequence exists, of course. We have, you can see, we have beautiful dots. Yes, but no, the sequence is divergent, which means the limit doesn't exist. Okay, let's solve maybe this one, because I can also show you one thing, and then this one, hang on. Okay, I do have, 5 minutes, okay, just 5 minutes, and I will let you go. Okay, for example, this one, evaluate the limit at infinity of the sequence ln of n over n, okay? Of course, you recognize from yesterday, if I will say ln of x over x is the infinity over infinity, you may use the L'Hopital rule and so on. Or you may probably know, do you think you can tell me the limits? Comparing the function, because ln of n and n, I can actually say ln of x and x. Which function grows faster? Because we can use the relative growing rates. Yeah, which function grows faster? Of course, n, because this is ln of x and this is x. And we can see how fast, how high is x. That means this is greater. If the denominator is winning, always the limit is 0. But of course, if you don't feel like it, we probably have to know all of these comparisons later, but you may also use the L'Hopital rule. Yeah, because you have infinity of infinity. But now, I typed, if you will decide, like if you, let's say you will have open-ended question and you will decide to use the L'Hopital rule for the sequence, some of the mathematicians, they can't stand looking at n, and then they will see the solution with the L'Hopital rule. Because what's happened, the L'Hopital rule, involves derivative. That means n is not really a continuous function. Where are my dots? I can use this. Because I do have ln of n, but I have ln of 1, ln of 2, ln of 3, ln of 4. That means I only have these dots. 1, 0, 1, 2, 3. We know the pattern, but we have dots. If we have dots, we have discontinuity. If we have discontinuity, we can't differentiate. That means, of course, we still, as I said, follow the same pattern. Everything works. But what they only want, probably you will think it's silly, they want you, and I am also one of them, just to rewrite the same question in terms of x. Because as soon as you see x, then you will think, oh, okay, it's continuous function. Okay? But yeah, it's one thing that I want you to be aware. I have to tell you. And that means just don't apply. I will, if I will give you the open-ended question and if I will see that you're still keeping n, it's fine. But please, please remember to rewrite in terms of x. And I can quickly apply. I can say h, the L'Hopital rule. X goes to the infinity, derivative of this, 1 over infinity, 1 over big is small. But of course, we don't even have to do it if we know the answer right away by comparing the function. But please just, remember that if that rule, the L'Hopital rule is applied, rewrite everything in terms of x. Okay, now another limit. Oh, of course, I'm just, oh, this is actually the nice proper question. Determine whether the sequence is convergent or divergent. The only thing that you have to do, compute a limit. How this behaves? Of course, you have the answer. -1, +1, -1, +1. It's jumping, it's oscillating. That means the limit doesn't exist. It's simply divergent. Okay. Oh, I think we did this one. Do you remember? What is this limit? Limit -1 to the n over n. It's 0, because it's like a nice snake. Okay, and it's convergent, of course, convergent to 0. Convergent to 0. Sometimes we will say it's like approaching 0. Okay, what else? Okay, and then it's starting formulas. I have this one. Okay, let's see. That's, yeah, I have this one. I have this one. I have this one. This one is solved, actually. This one is solved. Okay, let me pick. Shall we solve this one? I mean, probably what we will, yes, okay. You really have to check. You really have to check practice with Kasia, but I can show you. Okay, let's just solve this. Determine whether this sequence is convergent or divergent. That we have to compute a limit. Sine square of n 3 to the n. And since I see the sine function, I can probably use the squeeze theorem. Oh, no, let me start with sine. Sine of n, of course, is between -1 and 1. When I square, all of the square quantities are positive, greater than 0, but squaring the maximum value 1, I have 1 again. And now I will just divide each term by 3 to the n, because that's my formula. Okay, this limit is 0. 1 over big number is 0. That means the middle one is 0, based on the squeeze property. Okay. If you would like to think a little bit faster, of course, that's the idea behind, but you can think, okay, sine square of n. Sine square will have maximum value 1, yeah, because sine square looks like that. It's 1. 3 to the n, it's huge number. That means theoretically we have 1 over infinity. Of course, it's 0. That's not really proper notation, but that's how we can think that numerator is not growing at all. It's just 1. Even if we go further and further to infinity, this is huge. Yeah, that's exponential. I mean, it's a 1 over huge number, 0. But the squeeze theorem gives us nice solution. Okay, let's see what else I have. That's not important. Okay, limit of sine of pi over n. That's my sequence. In order to solve this, since sine is, I can focus on the inner function, okay, because I can focus on the inner function and then apply the outer function. That's how the limit could be defined. Okay, what is limit of pi over big number? Pi over infinity, pi over n. Yeah, any number over infinity is 0. What is sine at 0? Of course, 0. Yes, yeah, that's what we can see. I'm just showing you that you have to focus on the inner function first. Yeah. The same, chapter 1, but I know that we may forgot a few things. Okay, another sequence. Okay, this one is important, and this one, no, okay, but this one is nice, because if you will think about the inner function, yeah, like we have n times pi. That means it's actually infinity. Okay, it's actually infinity because it's 1 times pi, 2 times pi, 3 times pi, 4 times pi. It's discrete, it's just the dots, but it's still infinity. But I would like you to see something. Okay, cosine of 1 pi, right? This will be the first term. Cosine of 2 pi. You will give me the values. Cosine of 3 pi's. And cosine maybe of 4 pi. Who can tell me the numbers? Let's start. Cosine at pi. What's cosine at pi? Oh, 1, 2, 3. No, we don't have values of trigonometric function greater than 1. The trigonometric functions are between 1 and negative 1. Cosine at pi is negative 1. Okay, cosine at 2 pi. 2 pi is actually 1. Am I right? Yes. 3 pi? Negative 1. 4 pi? Positive 1. Okay. That means I can tell you none of the other like combination of cosine, sine, tangent, cotangent, n pi, n over pi. No. Only cosine of n pi behaves exactly the same like this. Okay? Remember, you can try because I always have students, they asking me, what about sine of n pi? What about sine of pi over n? Or no, none of them will create this beautiful alternation. Okay, that means sometimes if we would like to I don't know, check you, instead of negative 1 to the n, we will put cosine n pi. But it's exactly the same thing. And of course, we know that this limit doesn't exist because it's oscillating. Okay? But remember, that's the message. That's my message. Okay, and what else I have? Oh, you can probably tell me right away. Limit of this at infinity. What is 1 over n? 1 over infinity. 1 over infinity, 0. What's the final answer? The final answer is 1. Yeah, that's what you can see. This limit, this sequence converges to 1, if we would like to. Okay, I still have a few things. Okay, and you can check the solution of this one. You can check this one. This one is tricky. Okay, never mind. Let me switch my camera on. I will finish the session because I don't want to be too long because then it's not effective. Okay, that means one thing. You probably know everything about the sequences. One thing that I didn't cover, I didn't say, it's some formulas that includes something like that. Do you know what is n factorial? Okay, if not, it's okay. It's just simply multiplying numbers 1, 2, 3, 4, and reaching n. For example, 5 factorials will be 1, 2, 3, 4, and 5. Yeah. Or we can go the other way, right? We can go starting from the highest number. Okay, that means 1, because some of the formulas for the sequence will include factorials. And what I did, please check, practice with Kasia, factorials only. I'm explaining the factorials and solving important exercise. That means you will have this, and basically that's everything. I do have one formula that I really like you to know. I did solve it. Okay, I will put the short video about this because this formula, this one, n plus 1 over n, which probably you did yesterday, 1 plus 1 over x, is the same thing. That means when you use the L'Hopital rule, because we have to use the L'Hopital rule, it's 1 to the infinity, okay? You will get this limit equals to e, okay? And that's because it's e, it's a definition of the e number. That's when we also like this formula, okay? And probably I did something, I can double check, but this is the only thing that I want you to know also. The factorials are missing and that formula, Okay? If you compute, you can go through the L'Hopital rule, the power form, okay, and try to get E. Another combination that we can add, you can see I can change the number A. I can change 1 in the denominator for number A, and I can also add a coefficient B, coefficient A and coefficient B. And when you will go through the L'Hopital rule, solving this limit, A and B are affecting the answer this way. Instead of the answer being just E, is E to the power of A times B. That means, please, you have to know this, and you have to know this. Okay? Because that's the important formulas. Okay, that means I will finish the session, check the factorials because it's a big part, and then we're done for today. Okay, for 11.1. It's quite long, but that's always 11.2 will be also quite long session. Okay, rest of them will be a little bit lighter. Okay, thank you very much. And if you like the 11 a.m., I can keep the 11 a.m. Okay. Of course, if not, I will try. But if I will not get any message, any complaints, then I will keep 11 a.m. Okay. Thank you.